I acknowledge the traditional owners of the land on which I reside and pay my respects to their elders, past, present, and emerging. Also, since I was not born on or grew up on this land, I need to also acknowledge the traditional owners of the land from where I come, the Thylacine people. Hi, everybody. I'm Douglas Rovinsky, and today I'm going to talk to you about the thylacine, convergent evolution, and what that can tell us about this extinct critter. Now, the thylacine is a classic case of convergent evolution between distantly related animals, so much so that it's reflected in one of the common names, the marsupial wolf. This concept of convergence is so ingrained that the thylacine is often seen as little more than a wolf with stripes, a pocket, and a fancy paint job. This concept of wolf or dog convergence has had a profound effect on how we reconstruct the functional ecology of the thylacine, since we use the idea of convergent evolution, like between these swordfish analogues, to infer the ecology of extinct animals by comparing them with the morphology, functionality, and subsequent functional ecology of that living analog. Now, that's how we normally view the thylacine, right? As a marsupial equivalent to the wolf. But what if that isn't right? What if the wolf isn't the best analog to infer the thylacine's ecology? And how can we better frame the concept of convergence to more clearly understand the ecology of the thylacine? Now, convergent evolution is the independent development of similar phenotypes by separate lineages. This can be represented as evolutionary patterns within morphospace, where separate lineages converge on a similar area. But there are special cases of convergent evolution, like parallel evolution and incomplete convergence, where the different lineage tips move into a similar area, but they don't actually converge on the same morphology, as in this example of gliding mammals. Now, this can be due to various reasons, from the complex interactions of many-to-one and one-to-many form-function mappings, or historical inertia along the evolutionary lineages. Now, this spread in the pattern of morphospace is important to consider, as there may be many tips occupying this convergent space. And with the thylacine, that means dogs. And there are a lot of them. In fact, it's dogs all the way down. And these dogs all have very different ecologies from each other, which means that knowing which animal is the most precisely convergent with the thylacine and what that animal does is really important. So, who is the thylacine most convergent with? And what can that tell us about its ecology? Now, I looked into this in a paper published earlier in this year of our Lord, the pandemic, where I scanned the skulls of 56 comparative species across terrestrial faunivorous mammals. I then used high-density 3D geometric morphometrics to explore the shape of the entire cranium and also separated out the facial region, since, it's where the biting happens, and the neurocranium, since marsupials are infamously less endowed in this area. This allowed me to separate these kind of major confounding factors as I went forward with my analyses. So here's that all-important pattern in morphospace, with the thylacine here pretty far removed from the rest of the marsupials. Now, if we just look at the face, we see a similar story here with the thylacine, but a different pattern occurs when looking at the neurocranium. Now, I took these PC scores and I had the computer tell me who it thought it looked closest to each other, and then use this cluster of species as my likely suspects for convergence testing. Now, I used two different methods of testing convergent evolution. First, the standard Staten method, which uses scaled Euclidean distances between the tips and scales them by the maximal distance between those lineages. The second, newer Castiglione method computes a multivariate vector from the PC scores and then tests the angles created by the vectors, scaled by the time distance, not the Euclidean distance. So this test incorporates evolutionary time, while the Staten test just looks at the raw difference in morphospace. I then said, hey, if you're significantly convergent in both tests across the entire skull and the face or the neurocranium, then you've got a pretty good reason to be considered as maximally convergent with the thylacine. So, was it the wolf? No. Instead, it was these four canids, the maned wolf, the blackback and side-striped jackal, and the pampas fox, all of which are mesopredators focusing on prey much smaller than themselves. This can be seen when comparing the similarity of the mean skull shape of the four convergent species in the middle here with that of the thylacine, particularly in the bitey front half. Now, this is borne out ecologically too, as the shapes are significantly correlated to the preferred average prey size. Now, here it's important to note that there is a disagreement between the face and the neurocranium regarding the marsupials. Now, this has been noted in previous studies, like the Rowe et al. Bite Club paper. And, hopefully someone mighty clever can help make some sense out of this. So, what does all of this convergent evolution talk say about the niche ecology of the thylacine? Well, there's little support for it being much like a wolf. Instead, it very much seems like it functioned as a mesopredator, hunting small mammals. Also, maybe the thylacine shouldn't be seen as a classic example of convergent evolution, but as a powerful example of incomplete convergence. And at the end of the day, who was likely to be afraid of this marsupial wolf? Bandicoots, pademelons, echidnas, and bilbies. Oh my. So, thanks for listening, and I'll be around for questions. Cheers.